key.
How RSA works. So we have two numbers, which are P and Q. Both of them are prime numbers and are the foundational building blocks of RSA. RSA has a number of formulas which we need to keep in mind. First one is the N, which is the product of multiplication of P and Q. The next one is the totient of N. In other words, we called it as a modulus, and it actually helps us to identify the key size of RSA. It goes like this: P minus 1 multiplied by Q minus 1. The next thing is we need to identify the E, which is the exponent, and the interesting part of E, it must be between 1 and the totient of N, the value of it. And lastly, we have to identify D, which is the private key, and we identify it by inversing the E with the modulus of the totient of N. Once we have all these formulas, now we can actually establish what we are going to call as a public key and a private key. So the public key consists of E and N. However, the private key consists of two components, which are D and N. And here's how we actually encrypt and decrypt our text. We take the plain text, usually in a form of a number, raise it up to the power of V with a modulus of N, and we end up with a ciphered plain text. And for the description, we actually take the ciphered text, raise it up to the power of D with a modulus of N, which is our private key, and end up with a plain text back. Let's see an example for that. We'll take the P, which is equals to 11, and Q, which is equals to 13. First of all, we need to find the N. We'll take the 11 multiplied by 13, and that's how we get 143. Next thing is to find the totient of N. It actually helps us to identify the size of RSA, the key size of RSA. There are two ways for us to find it. The first one is a tedious one, and the second one is a quicker one. The first one is just to list down the numbers starting from 1 until the N, which is 143. But the easier way is just to use this formula, which is P minus 1 multiplied by Q minus 1. So we end up with a 10 multiplied by 12, and it results in 120. We also can call this number as a coprime number. Next thing for us is to find the E, which will be our public key. So to find it, we actually need to meet the requirements for E. It must be between 1 and the number of totents of N, so between 7 and 120. I decided to use 7 since it met both the requirements. And for us to find the private key, we need to take the E, invert it with a modulus of 120, do the calculation, do the math, and we end up with this number, which is 103. Using the public key and private key, we actually can encrypt and decrypt our plain text. Let's take an example. Let's imagine we have a plain text that we want to encrypt and send it to the receiver, and the receiver then has to decipher it using his or her private key. So we'll take the plain text, which is in our case, let's say 9, raise it to the power of 7, which is our public key with a modulus of 143. That's how we end up with a number 48. And when the receiver receives this text, this cipher text, he would want to decipher it. For that, he needs to take the cipher text, raise it up to the 103 with a modulus of 143. This is actually the private key of a receiver, and as a result, he gets the plain text back. So what we've done here, we have taken the plain text value, we have encrypted it, and we send the encrypted value to the receiver across the wire. And when the receiver receives this cipher text, he will use the deciphering formula to decipher it against it, and he gets back the plain text value as a result.